Okay, welcome back. So I will continue my very basic course. And in fact, today is going to be even more basic than the first two lectures, at least at the beginning, because I did chapter 1 first, which was sort of an overview to state the modularity theorem. Then I did chapter 6. But now I'm going to do a survey of chapter 2, 3, 4. Very quickly in 1.5 pages. So that should take 2 or 3 weeks in a regular course. What can we do? And then I'll spend really a bit more time on chapter 6 on Jacobians and try and explain many of the objects that have been showing up regularly in this series of in this conference, in this workshop. So push forward on Jacobians, pull back on Jacobians. What are modular Jacobians, abelian varieties attached to modular forms, things like that. So basic definitions. Okay, so let's start. So I said chapter 6 of Dwyman Sherman, but I'll start with some very brief things. So the reason I'm doing this is because Jacobians are usually attached to compact objects, and we've been doing open modular curves all this time. We haven't compactified, right? So of course, everybody else has been compactifying and using Jacobians, but I didn't do that. So let me just do that. Okay, so let's go back to the very simple, the simplest modular curve ever. First one, H mod SL2Z. So I wanted to draw this picture because everybody knows it, but it's good to draw once. So there's a fundamental domain for H mod SL2Z, which is very well known, like this. This is the circle of radius 1. This is I. This is omega. 2 pi I over 3. Okay, so it turns out that this space basically has a unique representative in this space. The boundaries, there's some identifications. This is identified with this is with that. That's picture right at the beginning of every book. One more thing. This notion of elliptic points. So let me also briefly recall those, though I won't use them much. So it turns out that, so this notation means stabilizer. Tau is a point in the upper half plane. SL2Z is the usual group, and you're looking at all matrices which take tau to itself. Okay, so this is generated by minus the identity matrix when tau is not these two special points in the upper half plane, but if it is, then it's generated by, I hope I got these matrices right, some group of order 4, and tau is the identity, and it's generated by -1, 1, 1. There's zeros where I'm not writing entries. This is minus identity, I should say, maybe, when tau is equal to omega. Okay, so I've never really done this very carefully, but this space, when you, well, we're going to compactify it, but it doesn't look like when you identify these things, you're going to get something smooth, right? There are these corners. So a lot of time is spent in chapter 2 of the book in picking charts and showing that when you compactify this space with one more point, actually you get a smooth Riemann surface, we get a Riemann surface. And it's not so obvious even to me now, after 30 years of teaching this. So you have to sort of really pick some chart to skip all this. So let me just say that when you compactify, you get a smooth Riemann surface. So what are the cusps? These are the elliptic points of order 2 and 3. Elliptic points are points for which the stabilizers in PSL2Z have order more than 1. Two and 3. These are the two elliptic points. So the cusps are a definition. E1 QSL2Z, and small exercise, there's just one point here. You write it this way. Various ways to write this as fractions or as ordered pairs. Ordered pairs up to multiplication by non-zero scalars. So sometimes it's just called infinity. There's just one cusp, and x of SL2Z is then defined to be, we just add on this one point. So it's just the old y of SL2Z and union one point. The claim is that this is a compact Riemann surface. In fact, it's Riemann sphere by a specific function j, which I could have defined in one of the lectures, but I didn't. This j in the old notation is something like g2 cubed divided by delta, and delta is forgotten, but maybe it's g2 cubed minus 27g squared, g3 squared. Somebody can check that. So remember, these points were basically lattices, and so they basically correspond to some taus of lambda taus, and then we had defined these functions g2 and g3 for lattices. So, all right, so that's just P1C, and in particular, it's a compact Riemann surface. Genus 0. Okay, similarly, you have x naught n and x1 n, which have come up already in many talks. So here you have to add on a few more cusps, and Jan has been telling us how to count the cusps, etc. So I won't do that for x naught n. Maybe I'll write some formulas down for x1 n. The reason I'm doing x naught n is because you can restate the modularity theorem, which I stated in the first lecture, saying that every elliptic curve is modular. The L function attached to the elliptic curve is the L function of a modular form. You can restate it in this more sort of algebraic geometry language, or maybe even complex analysis language. So there's a holomorphic map, non-zero holomorphic map. From x naught n to E, given any elliptic curve over Q. So what does it mean to be over Q? So far we've been talking elliptic curves over the complex numbers, but we also did speak about elliptic curves over the rational numbers. So it turns out that if you have an elliptic curve with the complex numbers and its J invariant is rational, then it has a model over the rational numbers. It's an elliptic curve with the rational numbers. I'll just write that here over Q. What this means is IE. J of E belongs to Q. J of E is some E tau or something like that. Right, so you have an elliptic curve over Q, but you think of it as an elliptic curve with the complex numbers. And then there's a holomorphic map. I already wrote that, non-zero, of compact Riemann surfaces. Okay, so you can just rephrase the modularity theorem in this language. Map from one Riemann surface to particular Riemann surface of genus 1, as long as your elliptic curve, the G invariant, is defined over Q. Okay, so just a small remark. So in Diamond Dim, there are like 10 different versions of the modularity theorem. Each time he introduces a new object, he sort of restates the modularity theorem. They state the modularity theorem in that language. So maybe I'll just follow that notation. This is what's called a version. Modular curve over C version, XC. Right, so similarly, we have x1n, which is gamma 1n modulo the upper half plane union T1Q. There are finitely many cusps, not necessarily one. And I think I'm going to need this formula. So the claim is that the cusps of x1n are in bijection one correspondence with the following set, and it's set. So this is, I think, just making what Jan said a bit more explicit, computing what Jan said. Okay, so a little bit of a nested definition, so it's a little confusing. CD is in this set, modulo plus minus 1. Okay, and the map is the orbit of, okay, let me write this as a fraction now, but this is also A colon C in P1Q. I'm thinking that it's a fraction sometimes, so A over C goes to this particular element, C, D, D chosen such that AD is congruent to 1, 1, N. Sorry, AD is congruent to 1 mod GCD of C and N. This is the GCD, by the way, C and N. So I have a small note to myself that if A is co-prime to N and D is co-prime to C, and A is co-prime to Cn. Anyway, let me not, some computation I have in my notes, but point is you can solve for D. All right, so it's just a remark. The reason I'm writing this down slightly more explicitly in this case is that I'm hoping in the last lecture, I'm going to define some Néron n-gons, and associated to each such pair, I want to define a Néron n-gon. Okay. All right, so leave that for now, but anyway, we have this sort of bijection of the cusps with some explicit set of ordered pairs. All right, so now some more generalities, moving on maybe from chapter 2 to 3. So here's a theorem. You have a congruent subgroup. Here's a formula for the genus. So since it's a subgroup of SL2Z, you have a map from the modular curve for gamma to the modular curve for gamma that you have the same sort of definition. X of gamma is just H union P1Q orbit space under gamma. So suppose this map has degree D, then very nice formula. Put it here. The genus of X of gamma is given by the following formula. So these are the elliptic points, number of elliptic points of order. Orders is once you go plus mod plus minus 1. So order 2 and 3 there. Elliptic points of orders 2, respectively 3. And this is the number of cusps of gamma, or more precisely of X of gamma. So this is another very nice formula. And I think more important than the actual shape of this formula is how it's proved. So there's this Riemann-Hurwitz genus formula, which allows you to predict the genus of this. When you have a cover like this, it allows you to predict the genus. And if you haven't seen this, I learned this when I was a student, and Lazarsfeld was giving a colloquium on this to the students at UCLA. It's a beautiful proof. The idea is you triangulate. Suppose you have some triangulation here, right? It's not a triangle, sorry, but I'm working fast. Yeah, so you triangulate this, but you don't take an arbitrary triangulation here when you're computing genus. You take a triangulation which lifts this triangulation. In particular, there's some bad points of ramification. So you want to choose your triangulation upstairs so that maybe you shouldn't work with this one. You first work with the triangulation upstairs. Okay, so you make your ramification points as vertices and work with that particular triangulation. And then this formula becomes almost obvious from the genus, Herbert's genus formula. Right, because the Euler characteristic is 2 minus 2g, and the Euler characteristic in here and here differ by d, because the number of triangles is d, right? So work that out. Work that out explicitly, you will get something like this. And you can mentally check that when gamma is SL2Z, okay, let's do that. What are these numbers? So there was 1 point here of order 2, 1 point of order 3. The degree was 1, so this is 13 over 12 minus 1/4 minus 1/3, 1 cusp minus 1/2. And that number is 0. So on and so forth. Cross check. All right, so I think that's all I want to, maybe 1 or 2 more general things. So in chapter 4, there are also some dimension formula. Let me just say 1 or 2 of them. So it turns out, and this has been used also, that the modular forms of weight 2 and level gamma is gamma naught n or gamma 1n or any congruent subgroup, is just the holomorphic differentials on x of gamma. And therefore, the dimension of this S2 gamma, easiest dimension to remember is just the genus above. And then some Riemann-Roch stuff, which is pretty complicated when you first see it. Yields the following kinds of formulas. I'll just give some examples. So let's do, just to see what the shape of these things are. So k minus 1 times g minus 1. G is the genus of the underlying modular curve for weight 2, plus k over 4 floor epsilon 2, k over 3 epsilon 3, plus k over 2 epsilon infinity. K greater than or equal to 2 even. And there are also formulas in the odd case. I'm not writing the other formulas down for weight 1 and weight 0. I mean, sorry, this even anyway, but some other formulas, more degenerate cases. Let's do odd, a minus 1, over 3, epsilon 3. There's no epsilon 2, I think, this time. A over 2. Part of the reason I want to do this is I want to write these words down, regular and irregular. Minus 1 over 2, epsilon infinity, irregular. If k is greater than or equal to 3, odd. And maybe if minus 1 doesn't belong to gamma. If minus 1 belongs to gamma, you basically get 0. Okay, so what are these? So it turns out that when minus 1 doesn't belong to gamma, you can further break the cusps into irregular cusps and regular cusps. I think it's a mark of how well you understand modular curves is if you know these definitions and remember them. Last time I used this was maybe 15 years ago in a paper with Narasimha Kumar. I was not here, I think. So we had to do some computations. We really needed to use this. So I just wanted to put the words up there. There was a paper on Hira theory at the prime 2. And we had to compute some cohomology groups, group cohomology groups. Some of the answers were different, depending on some regular things. Okay, so similar formulas for SK gamma. I won't write them down. Okay, so you can't see over there, but I'm going to start a new topic here because I don't like to erase so much. So write big. So I'm finally moving to Jacobians. Write the title again. So all of this, what I said was some of the highlights from chapters 2, 3, and 4. Of course, you can go into much more detail than that. Jacobians. Let X be now we'll work more generally, not just with modular curves, but compact Riemann surfaces. X is the compact Riemann surface. Dimension 1. Omega 1x is the space of holomorphic differentials. It's dimension 1. Space of holomorphic differentials. I said that somewhere. On X, we just said the dimension was equal to the genus. We'll write it again. Okay, so to define the Jacobian, it was already done very quickly. Yeah, let me just recall it and also explain two different formulations of the Jacobian in terms of divisors, one in terms of some integration theory, differential forms, both the same by some famous theorem of a Jacobi. And you can move from one language to the other. Sometimes formulas on one side are easier and more difficult on the other, etc. Okay, so that omega 1x dual hat. Okay, let's follow Diamond Sherman as much as I can. So I think they write upper hat for dual. So this is just the dual space. Linear forms on omega 1x. And first homology group H1xz maps to this dual space by taking sigma to, you have to find what happens to a differential form, you just integrate. Omega goes to integral mu over sigma. I think it's simpler than that. These are what are called periods, basically integrating differential forms against cycles. The definition of the Jacobian, first definition, is image of H1xz inside omega 1x hat. That might even be an injection. I haven't thought about it. I think it has basically an injection. It is torsion free. So I'll just identify it with its image. This is the Jacobian of X. First definition of it. There's an alternative formulation, which we'll get to, or we're getting into it now. So what is this? This is like, this is a G-dimensional complex vector space, right? Because omega 1x had dimension genus, which was G. Dual will have the same thing. And then you have some lattice inside here of rank 2G, right? Everyone computed this Mohali group in their classes in topology, I guess. We did the case G equals 1 in detail. Just C modulo a lattice of rank 2. Okay, so another formulation of this. Is we work with divisors, degree 0 on X. So let me just define these formally. I don't think I ever did or anyone did. It's just formal sums, summation nxx with nx almost always 0. First of all, nx in z, nx equal to 0 for all but finitely many x. And anything else? Yeah, the sum is 0. Sum of the coefficients is 0. Divisors of degree 0. So this is sitting in all divisors. So there's a subset of this abelian group. This is supposed to be an L for linear equivalence. These are special kinds of divisors of degree 0, ones which measure the poles, orders of poles, and zeros of meromorphic functions on X. So, definition. So there's various notations. Some people call these principal divisors and then write this notation, or almost looks like a principal ideal. We'll write div F. F is a function on the meromorphic function on the on X. Okay, and then the card group, pick 0. So it turns out that's a theorem that these divisors have degree 0, right? Order of vanishing of poles and of zeros is the same. Just count things with multiplicity and all right. So then this is a sub of this. You take its quotient. So we get some sort of abstract abelian group. A little tricky to see what it is exactly, right? There's some abstract abelian group right now. But the claim is that this is another way to write the Jacobian. So, theorem of Jacobi. Pick 0 is the same as the Jacobian. So the maps from basically the integration map. Make my heads go the wrong way. So this taking a divisor of degree 0 to the following linear form on omega 1x. Writing this a bit abstractly. So this means you integrate differentials. Just writing the integral, not writing omega maps to the integral of omega. Fixed base point. What is a fixed base point? So this map induces an isomorphism of abelian groups. Pick 0, the Jacobian of X. So there's some things to check there. You have to basically check that the denominator is going to the denominators on both sides, right? That's first of all to make that well defined, and then that it's an isomorphism. So I'm not going to get into the proof. I don't think it's even there in dimension. This is a well-known classical theorem. And yeah, some remarks. If the genus is 0, then the right-hand side is 0. And therefore, right, because there's no dimension here, and the left-hand side becomes 0. And that shows that every divisor of degree 0 is principal, right? So that's true on P1C. You recover a classical theorem in complex world. Okay, so here is another version of the modularity theorem using Jacobians. This is what they call version JC. And I think this was also mentioned today. So I should have said there exists for every E, there's a map and an N, etc. But anyway, quantifiers I'm dropping. All right, let me just let J naught N be the Jacobian of X naught N. It wasn't officially defined, but yeah, given an elliptic curve over Q, there's a non-zero holomorphic homomorphism get that here, non-zero holomorphic homomorphism on 2. So given an elliptic curve, there's a non-zero holomorphic homomorphism if your elliptic curve is defined over Q. You take the complex points here and then you map like this. J invariant is a complex curve. The J invariant belongs to Q. It's a model over Q. You always find such a map. The holomorphic homomorphism of complex tori. Non-zero holomorphic homomorphism of complex tori. Okay, so that's yet another formulation of the modularity theorem. Okay, so I think one of the main sort of themes I was trying to unify the 4 lectures with some common topic, and that common topic was integral structures on spaces of modular forms, right? So integral structures which are preserved by the Hecke algebra. So the first thing we need to do now is we want to prove that theorem using Jacobians. And as someone pointed out, that this proof only works for weight 2. Okay, it's maybe a little simpler than Shimura's general proof using the Eknath-Shimura isomorphism. But anyway, it's only for weight 2. So what we need to do is first make sure that we try and understand how Hecke operators act on Jacobians. So we know how Hecke operators act on modular curves, but what about on Jacobians? So I'll do some generalities first and then tell you how the double coset operator acts on the Jacobian section. So I'm going to restrict to the card group side and spend another 15 minutes doing it on the complex torus side, on the first definition of the Jacobian that I gave. Let's just pick one and do it there. That's the one that's more natural from the point of view of these lectures, because we already saw the Hecke operator as a correspondence on the modular curve. So induce maps on divisors of degree 0, etc. So let's do that. So some generalities. So fix a map H from X to Y of Riemann surfaces on constant holomorphic map compact Riemann surfaces. Dimension 1. I may forget to write dimension 1. So first of all, H lower P, P for Picard, and there's H upper P. And then once you get good at this, you just drop that all together and write H lower star and H upper star. And these were some of the maps that already appeared in, for example, Samuel's lecture, maybe in Jan's, I'm not sure. They were certainly there all the time. Okay, so what is this H upper P? Give a definition. So for that, we first need to write down an induced map on meromorphic functions going forward. So given a function f here on x, how to get a function on y? It's given by this formula. Define it to be the product of the following values. Take all preimages of y under x, under h. So there's a bunch of x's, and then you just take f of x. And as I said, there's sometimes these ramification indices, which are mostly 1. But if you want your formulas to work, then you need to put them in. Okay, so turns out that we have the following nice V of y is the order of vanishing at y, evaluation of some kind. The norm of f is just the sum x belonging to H inverse y of Vx of f. So why is this true? I mean, this is just something in local charts. Let's do an example. Suppose you have this function is y equals x squared. The ramification index is 2. 0 goes to 0. I'm just taking a simplest baby example. And suppose you have something like x goes to x to the 7 here. You have to figure out what happens to this function under that operation. What does y go to? Well, we know that y is x squared. So what happens to y? Well, x goes to x to the 7. So y is going to x to the 14, right? But x to the 14 is also just y to the 7. So this function is just y to the 7. So somehow the order of vanishing, right? Because of this 2, this becomes x goes to x to the 14, this function. 0 goes to 0, but that's just in y, it's just y goes to y to the 7. So the order of vanishing doesn't change under this. This is the way I justified it to myself. Please tell me if I'm doing something stupid. Okay, then we have this formula. So based on this formula, we now, so let me just summarize this. So therefore, the divisor, let me write divisor because there are too many round brackets maybe. The divisor of norm of f is given by just the sum over y, what is the definition, by of norm of f, y, which by this formula over here, we'll write as sum over y from x belonging to H inverse y, the xf, right, that was that formula over there, times y. So we have this little computation that the divisor of the norm of a meromorphic function is given by this formula. One more step maybe. Let's write this as summation y x. Get rid of y altogether. So summation x, the x of f, right? If you're summing over y and then all pre-images, you can just sum over all x's. And y is h of x. So we can write this as h of x. Little computation. Okay, so it's needed because I want to define a map on the numerators, rises of degree 0. Yes, any questions? Maybe label this as star since I'm going to wrap around. So let's define HP. So HP, the map is the obvious map because you have a function from H from X to Y, which I just erased. You just should push forward divisors using H. Define, check the denominator goes to the denominator and that star will do that. So define HP from divisors of degree 0 on X to divisors of push forward maybe, H lower star. Calling it H lower P for Picard. Just sending summation NX dot X to summation NX dot H of X. This is some sort of Y. You take the coefficient to be N of X. And you can see from star, I can't see, but you can see that F maps to the principal divisor norm of F, I hope. right? Because if you replace f is summation Vx f times x, and if you take the divisor of the norm of f, exactly this formula, right? You start with the summation Vxf times x. You apply the h to the x's, they just become h of x's, right? So the divisor of norm of f, divisor of f maps to the divisor of the norm of f. So this induces the map on x0. Right, this is a degree 0 linear equivalence. Okay, so that's wasn't too bad. There's a similar recipe for pulling back divisors. Let's call that H upper P. So how is that defined? So that H star be the pullback map on functions. Sorry, be y to x now. H was a map from x to y. Better write it again. Pullback functions for H. That's H star. And clearly, let's draw a picture again, maybe. The pullback of H of G, order of vanishing at x, is this time the ramification index times okay, so similar kind of picture. What's going on here? You have locally there's just this and 0 going to 0, and suppose this map again was y equals x squared. And this time you start with the function y goes to y to the 7 on this side. Then you see that you will go x will go to x to the 14. And this is a map x goes to x to the 14, right? So that ramification index is what gets multiplied when you look at the order of vanishing. So we have this formula. Okay, let's do a divisor computation. What is the divisor of H star G? So G was a meromorphic function on Y. H star of G is a meromorphic function on X. Let's look at its divisor. So a small computation. So by definition, it is of the form Vx of H star G times X, right? That's what the divisor is. Order of vanishing at all these points. Use this formula above here. You can write this as Ex V of H of X of G times X, which we will rewrite as summation Y belonging to Y, Vy of G, changing notation from X to Y, H of X is Y. And then let's write all pre-images. They were common here. Let's move the Ex inside. So X belongs to H inverse of Y, Ex. And just rewrite that formula in this way using Y's instead of Y outside. And X is inside. And finally, we can, so this formula shows, therefore, okay, so first write the map down. That double star maybe. Okay, so that's finally defined. H upper P from divisors on Y, it's going the opposite direction this time. Divisors on X by the following formula. So this is a little less natural, maybe. The first map was much more obvious. You just applied H on the X's and you didn't touch the coefficients. So then you have to think a second. before you write it down. So what is it? Summation ny times y. What do? You map it to summation x belonging to h inverse y ex dot x. Okay, so that's just a formula that it's being told to us. So that's what it is. And we have to check now that it induces a good map on the denominators in the Picard group. So if you have summation ny vy, summation nyy, but this is the principal divisor, so ny is just vy of g. And what happens to it on this formula? It goes exactly to this, right? Ny is vy of g, then this shows that G, principal divisor G, maps to that's very nice. So therefore, we get an induced map on the Jacobian. We'll also call H upper P. From the Picard 0 of y, pick 0 y to pick 0 of x. Well-defined map. Any questions? There's just definitions. This is a degree D map, so there will be finally points in the fiber. Yeah, the map of compact Riemann surfaces. There can be some collapsing. You can have maybe just 1 point in the fiber, but at max you can have D points in the fiber where D is the degree. This EX is meant to normalize for such things, and there are many small checks you can do, but you're asking such questions. For example, it's not totally obvious, for instance, that you have a divisor of degree 0, it goes to degree 0, things like that you have to check, right? So I'm going to leave some checks for you here. Kind of obvious because summation ny was 0. Why is this sum 0, right? You have to check that. But you have to use the fact that summation ex is equal to d. You add up all the ramification indices d, so d will pull out, etc. And just check some small things like that. Other questions? Okay, so one remark here is, it's not really needed in this course, I think, but who knows, maybe it will be used. Let me just say that if you first pull back and then push forward, then you get nothing but multiplication by degree. Let's maybe do this with computation. So proof. Suppose you have summation nyy, and you first pull back and then push forward. So what happens? Well, we already have the definitions on the board. I think both of them are here, I hope. So the first one is right here. So apply, you get summation ny, y belonging to y, summation x belonging to h inverse of y, ex times x. Right? HP on that. And HP was a very simple formula. All you do is you skip all the coefficients and just apply H here straight, right? The H formula is very simple. This one, the first pullback is a bit trickier, but push forward is very simple. So you get summation y belonging to y, ny, summation ex, h of x, x belonging to h inverse y. Okay, so this is just because x is an h inverse y, this is just a y. And now you can rewrite this as, I'm going to use summation ex is equal to d. This has become a constant now because all these points in the fiber have the same image. They're just y. This number becomes d. Pull that d out. Summation y belonging to y and y. Since summation ex is equal to d. Okay, so those were some generalities that I wanted to do. So for example, this paper of Matthew Baker came up, and to understand all the formulas that you need to understand things like that. So it's basic language. All right, so let's now get to number theory. These were generalities on Jacobians. Back to number theory. Let's see how the Hecke operator acts on Jacobians using this language of push forward and pull back of devices. A really nice eraser wasn't here yesterday. So Hecke operators on modular Jacobians. Okay, so let's recall some things again. So recall at omega 1, holomorphic differentials on x of gamma. I'm going to use some obvious notation now and not write gamma as a congruent subgroup, etc. each time. Isomorphic to S2 gamma. By the way, you might wonder why there's an S2 there and not an M2 there. This is F going to F of Z dz basically, right? The problem is that if you write it in terms of Q, dz is just dq over Q. If F is holomorphic at 0, you'll have a 1 over Q term there, and that won't be a holomorphic. You have a holomorphic modular form, M2, right? Starting with the Q expansion of Q equals 0, you have a problem because it's dq over Q and starting with a Q expansion starting with a Q. So really that you really needed that you have a cusp form so that you can cancel one Q and get something that looks holomorphic. Okay, so right, so you can maybe also recall the definition of Jacobian. X0 of x of gamma we said was equal to Jacobian of x of gamma, other Jacobi thing. And this was S2 gamma. Generalized definition of mod cusp forms. Upper hat mod H1 xz. X of gamma. Z. Okay, so this is what we had in some notation. So by lecture 2, we had defined some double coset operators on divisors. Give 0, y2. So suppose there's a gamma 1 and gamma 2. I won't write everything down. So you have all these analogs for gamma 1 and gamma 2. So we had already defined such a thing. We had actually divided it on all divisors, but you can check that degree 0 divisors go to degree 0 divisors, right? We had to find a double coset operator using that kind of square, right? Inverted horseshoe that I drew here. You take a point, you take so many pre-images, you push it over and push it down, right? So that gave a map on points. It was a correspondence and induces a map on divisors. takes divisors of degree 0 to degree 0. And we can just extend this to the compactifications. Same formula. Pull back, multiply by alpha, and push down. In terms of that square, we had this auxiliary x3, it was y3 in that notation, but compactify in the usual way. So we have x3 prime. So I'll just assume some notation here. We had x2 here, and we had x1 here. Let's give these maps some names. Let's call this pi2 and pi1, I think. Yes. It's induced by multiplication by alpha. So in terms of this picture, and in terms of these two maps, h upper p and h lower p, what is the Hecke operator? Pull back, multiply by alpha, and push forward. Right? So in terms of this, we have the obvious formula that gamma 1 alpha gamma 2 is given by pull back first under this map, pi 2, multiply by alpha, and then push forward by pi 1. Picard. Upper P and lower P were the notation I just defined for those particular maps H. Right? This was the definition of the Hecke operator in terms of these two maps. Okay, so now we managed to write the Hecke operator in some general way on the Jacobian. Just pull back and push forward, but there's the multiplication by alpha. Okay, so this is on the Picard side, the Picard definition of the Jacobian. What is the induced action on the actual first definition of the Jacobian? As dual of omega 1 modulo h1. Oh, yes. I should have said here that, wondering why I was writing this notation again. So I'm doing a slight change here. I'm identifying omega 1x with S2 gamma by that. I was recalling this notation, it didn't occur to me when I was writing it down from my notes. So I'm going to use this formulation. Instead of writing omega 1x dual, I'll write S2 gamma here. Okay, so S2 has some intrinsic action of the Hecke operator also, right? Which we defined with the double coset. When you push this action over to the other side, to this side, could it possibly have anything to do with the natural Hecke action on S2 already defined, right? On modular forms. If you have an action on modular forms, you have an action on the dual spaces also, right? You have an induced action on the numerator, etc. So here's the proposition first, which I won't prove. You have to check this. Indeed, everything is very nice. And this action on divisors translates to a very natural action on the other side. So proposition. If gamma 1 and gamma 2 are just gamma 1n, so let's do the Hecke operator TP. And alpha is 1, 0, 0, p, right? Then gamma 1 alpha gamma 2 is just my definition TP. We saw that yesterday. It was defined to be this double coset operator for the matrix alpha to be 1, 0, 0, p. Let's write J1 of n, since I only define J0 of n to be the Jacobian of x1n. Obvious notation. Then TP, that TP over here for this particular alpha TP on the left in this setup induces a TP on the right. Left and right means, maybe I should say the second and first formulation. So TP in the second formulation, which is defined over here, induces the TP in the first formulation by the Jacobian map. And what is that TP in the first formulation of the Jacobian? Given by the obvious thing. It takes a linear form phi to precompose with TP. The phi is a map from the space of cusp forms to the complex numbers, right? It's a linear form on the space of complex numbers. You first make TP act on the space of cusp forms, and then you compose with that linear form. This will give you a linear form on S2 gamma. And the claim is that everything is well defined, etc. So this is a proposition that's proved in Diamond-Sherman. Let me assume this, that TP on the right becomes, sorry, not right, but in the second formulation becomes very natural TP in the first formulation. Okay, so we can now finally deduce the first proof of the fact that the matrices of the Hecke operators can be chosen to be in Z by choosing your basis intelligently. So how does that go? Now we have 0 going to H1 X1N Z. This is the definition of the Jacobian. S2 gamma 1N I'm writing as a short exact sequence. Right, that's the definition of the Jacobian. Right, numerator in the middle and denominator on the left, and the quotient here, J1N. And let's write another copy of this. We just saw that the TP, which was on the Picard group, induced a TP in this formulation, first formulation of the complex torus operator TP. And we just saw in this proposition that the TP induced on the Jacobian is actually just given by on the numerator, something on the numerator, right? Coming from a map here, the obvious map TP here. Calling it TP, but maybe TP dual. Let's just call it TP. Transpose. Okay, so the TP map here is actually coming from TP here. That's the content of the proposition. And therefore, it's forced to take this kernel to this kernel. If you restrict this TP to this because of this community of this square, this TP has to go to TP. Okay, so that's it. This is the little check. You can do a diagram chase there when I'm wondering what to say next. But okay, so conclude. TPs act by matrices defined over Z. And therefore, their eigenvalues are algebraic integers, right? Cayley-Hamilton theorem, it's just a polynomial defined over Z. So the eigenvalues are algebraic integers. And we said last time, though not very clearly, these eigenvalues are exactly the Fourier coefficients of eigenforms. As long as you do some normalizations, you need to make the first Fourier coefficient equal to 1. Right? These are exactly so that shows that the Fourier coefficients of modular forms are also algebraic integers. So this is the proof in Diamond-Sherman of the algebraicity of the Hecke operators. And as I said at the end of last lecture, if you want to go to all weight K, you can use something a little bit fancier, but similar principle. You can look at a group cohomology group, parabolic cohomology group. So most people actually take complex coefficients here and take 2 copies of S2, right? And that's the way that you'll see it in many books, but this is a slightly simpler way, but a little more confusing because the real numbers on one side and complex numbers on the other side. But this also works. Make the real part of some cocycle. Sk. So now suppose k is not 2 anymore, k is greater than or equal to 2. What would you do? Well, as someone pointed out, this proof doesn't work. There's some Jacobians and weight 2. This is a weight 2 proof. And anyway, this conference is a weight 2 conference, in case you haven't noticed. Right? But yeah, but you could try and ask things for weight k also. And so what would you do for higher weights k? Well, we said this last time. It's very similar. You look at sim k minus 2 z squared. Right? The image of h1 z squared sitting in h1 r squared. So contortion may be there, but it dies. You look at the image, call it h1 z squared again. And one checks that you can define this p is different from also a little p, but it's parabolic p. You can check that the Hecke operator is TP, not that p, TQ for q, all q's. They actually, there's a definition on cocycles. So the h1 is just functions from this space to this, satisfying some almost homomorphism property. You can check that you can, by double slashing, by slashing sum, you can check that the definition of TP actually takes and defines an action on H1, and it actually takes parabolic cocycles to parabolic cocycles. So what's a parabolic cocycle? A parabolic cocycle is one such that when you further restrict this to the stabilizers, so I do need stabilizers. I thought I was wasting my time by defining them. But if you restrict to stabilizers of all the cusps, right? There are finally many cusps, so you restrict to a direct sum over the cusps of H1 gamma S, same thing here, then these cocycles die. That's the definition of parabolic homology. There's a geometric interpretation in terms of what is called the Borel-Serre compactification of the modular curve. You don't add a point at each cusp, but instead you add a small disk. That's not a disk. Well, you add a disk, but then you remove the open disk, so you'd add a circle. Okay, so these can be just, these groups are basically Zs, right? It's 1, Z, 0, 1. Those are the stabilizer of infinity, right? So it's basically a copy of a Z. And that's pi 1 of S1. So these groups are basically just, these are just, yeah, H1s of the cusps. And yeah, so this has a geometric interpretation. Let me not get into it. It's very standard. We have a similar kind of sequence using Borel-Serre compactification of a modular curve, which we're not talking about at all in this this course. Some interesting story about the Borel-Serre compactification that just came to my mind, which I'll have to think about. But there was some issue about proving that the homology of an open curve is finitely generated. It's not so obvious. It's compact, it's obvious. So you wanted to somehow come up with another variety which had the same homotopy type as the original one. And so Borel-Serre, or Serre, somebody, one of the two, they use this compactification. The homotopy type doesn't change because you just have a, if you had a cusp there, the homotopy type changes. You lost loops, right? But if you replace your cusps by S1s, you haven't changed the homotopy type of your variety. So the hunt was on for a variety which was compact, had the same homotopy type as your open curve, and Borel-Serre found this nice variety. But interesting story, somebody at TIFR had actually proved this a bit earlier. So Raghunathan actually used Morse theory to actually prove this statement. So it's not a very well-known fact. But this was the reason that Borel-Serre was discovered. Okay, let's see. What can I do next? Yeah, so maybe I won't go too much into that Schmeiss. I keep forgetting to say this is a Hecke covariant thing, otherwise it's nonsense, right? You can't transfer Hecke eigenvalues from this side to that side. The natural Hecke actions on both sides is Hecke covariant isomorphism. How much time do I have? 15, 20 minutes, okay. So I'll make some remarks now and then maybe a joke. So let's see. We're running ahead of time. So some remarks to unify with some objects that appeared in the lecture. Oh, sorry, I missed a whole section. I also wanted to define, wondering why running ahead of time. I have a whole page more to do. So I want to define modular Jacobians. I said that at the beginning, but I was done. Not modular Jacobians, modular Abelian varieties. These A sub Fs that have been coming up. Okay, so modular Abelian varieties. You know, there's a fancier version of the modularity theorem, not just that every elliptic curve over Q is modular, but that every abelian variety of GL2 type is modular. Okay, so you take, there's a notion of an abelian variety of GL2 type, and won't maybe define it, but there's no modularity there, and the claim is that that is also modular, basically of the form A sub F. Okay, so what are these A sub Fs, first of all? Okay, so so we had T before, so this is the Hecke algebra over C, but now let's look at the algebra over Z, because we know that think of these as matrices in Z, generated by Tn in S2 gamma 1n. Correction from yesterday, I had said that something was self-adjoint, but I should have said normal. Those fudge factors are there in the adjoint, but it's still normal, the operator, so it's still diagonalized. So anyway, I'll add that to the notes. So we have this algebra, and what does it mean for F to be a normalized eigenform in terms of this algebra? Equivalent to saying that you have a homomorphism. So this is actually a subalgebra of the algebra, matrix algebra maybe over Z. So you have a homomorphism from taking En to An. An is this Q expansion. Normalized. 1 is 1. Okay, so this is almost a tautology. Somehow the eigen thing satisfied by the eigenvalues exactly the relations in the Hecke algebra, etc. So it's a map of algebras. Z map of Z algebras. And as people have used, and maybe even pointed out, maybe not the proof, but the image of that is just some ring of integers that came up this morning as Z adjoin omega, or maybe omega 6, remember, which would have unity, theta 6 maybe. Anyway, so it's actually a finite Z module. We don't get something. So if you look at the image of this and tensor with Q, we actually get a number field. You don't get a big field. People see why? Why is that true? Infinitely many ANs there, but you still get only finitely many things in the image when you tensor with Q. Think about it a second when I'm writing. Yeah, so the Hecke algebra is finitely generated. It's a subalgebra of the matrix algebra, right? So n square matrix, n by n matrices over Z. Rank of that can be no bigger than n squared over Z. So it's finitely generated, that much is sure. You can just take images of the generators and that will be the order that you will get inside Z bar. Those number fields are very interesting, but we're not talking about them at all in this course. So if I was to give a course parallel to Jan's, I would start talking about, for example, Q root 144169. You know what that is? No, it's the image of, so what happens is if you take the delta function and look at the image of this, all the Fourier coefficients lie in Z, right? So you just get Z. And then if you do this for the first 6 cusp forms, you always get Z. But then suddenly you get a quadratic field. That's the form of weight 24, right? And it turns out that the field of Fourier coefficients of that form is this. It's a dimension 2 thing over Q, and you get square root of 1. It's easy to remember that number because it's 12 squared, 13 squared. Times 1,000 somewhere, but easy to remember that one. Okay, so yeah, so these Hecke fields are extremely interesting, and I think not very well understood actually. For example, Q root 5 shows up a lot. People know why that's true. Actually, that's interesting in the context of this workshop. Why should this field be Q root 5 so often? I think Erikson once explained that to me. I think maybe you can confirm, well, one of the modular curves is rational, x15. So it's just P1C, so there's a whole bunch of rational points. And that's supposed to explain why you have, getting the proof now, but you have so many modular forms, or you expect to have so many more modular forms with Hecke field Q root 5. Maybe it is not the modular curve, but some Hilbert modular. I want Q root 5 to act on the abelian variety. So the abelian variety is a dimension 2. There's some space with multiplication by Q root 5, which is rational. It has a whole bunch of rational points, and that explains why Q root 5 shows up a lot, or gives some intuition behind why it should show up a lot. And cover that proof. Okay, so these Hecke fields are very, very interesting, but not much studied. For example, a lot of people just say, let this be E, let the Pierre completion be some finite extension of QP. A lot of arithmetic is lost when you do that, but okay, it's the way people do things now. So let IF be the following kernel. Kernel of lambda F. So being a sub-ideal inside the algebra, it acts on the Jacobian, because the Hecke algebra also acts on the Jacobian. So, right, T was acting on S2 gamma 1, and so it acts on the dual, so it acts on the quotient, etc. And I is an ideal, so it acts on J1N. And let me write N of F here to make it a bit more precise. So I'll explain that maybe a bit later. So even though N is general, the level of the form, there's some new form theory, may not be exactly N. It may be smaller, but anyway, S2 gamma 1 NF is sitting in S2 gamma 1 N, and the Hecke operators preserve S2 gamma 1 NF. So you can just think of the Hecke algebra acting on S2 gamma 1 NF. So therefore, IF J1 NF makes sense. Just take the images of all the things in the ideal and look at the span of them. Okay, so definition. Let's define A sub F to be J1 NF mod IF J1 NF. It's quotient variety, and this has an action of T of Z, E over Z, the Hecke algebra over Z modulo IF, which we said, we didn't really write over there. The Z module spanned by the ends, but this is a finite rank Z module, right? You tensor with Q, you get a number field, you don't get something infinite dimension, finitely generated. These kinds of rings showed up today in the morning. And the theorem is, this is proved in Shimura's book, J1N is isogenous, where isomorphic to product of these AFs, but with some multiplicity. So first of all, you don't take all Fs, you take Fs in S2 gamma 1 NF, new part. And square bracket F means Galois orbit. You take just one representative, I mean one form for each Galois orbit. These are algebraic integers. So if F is a new form, F sigma is also a new form, but you don't take those two twice. You just take one of them. You look at the abelian variety AF. You take some multiplicity where MF is equal to the number of divisors of N over NF. Okay, so you have a very nice decomposition of, at least up to isogeny, of the modular abelian variety, a modular Jacobian, J1n, as a product of these abelian varieties attached to the modular form. This is somehow called the abelian variety attached to the modular form, F. Okay, so that's the definition of A sub F. So some remarks about this. One of them has already been mentioned by Jan. Just say it again. The L function of AF. AF is a variety. You can create a zeta function out of it, counting points, mod P for all primes P. The interesting part of the zeta function is the numerator. Some H0, H2 terms on the top and H1 terms, if you think of it chronologically. But anyway, there's some interesting part is the L function attached to the abelian variety. So let's call that LSAF. Many ways to define that. Let me not get into it. So it turns out that LS, the geometric zeta function, the numerator of the geometric zeta function attached to AF is LSF. Almost, you have to take a product over all F in the conjugacy class. Sorry, the Galois conjugacy class. So if you have an abelian surface, it's a dimension 2, the Hecke field, number field generated by the Fourier coefficients is a dimension 2. You get two L functions here, LSF1 and LSF2, where F2 is F1 sigma, automorphism, quadratic automorphism. Okay, so that's one remark. To say a few other things. It turns out that the endomorphisms of this abelian variety. So here, there's a little Q bar here. I'm not just taking endomorphisms of the abelian variety. This abelian variety is defined over Q, by the way. The Jacobian tends to be defined over Q, and so is this. All these abelian varieties are defined over Q. But we take endomorphism defined over any finite extension of Q bar. And let's tensor this with Q. So this is called the cross product algebra. A classical object which was studied by Momose and then by Ribbit. And they completely, a cross product algebra is basically some finite dimensional algebra where the multiplication relation on the generator is given by some cocycle. Okay, so it's a central simple algebra. And so we expect it to be given by a cocycle. It turns out to be two torsion in the Brauer group of some F number field, which is sitting in the Hecke field. It's not exactly an element of the Brauer group of E, the Hecke field, but in a slightly smaller subfield. And Ribbit asked this very tantalizing question because by class field theory, you know, this is the direct sum of two torsions of the Brauer groups of all the completions, which are just, well, each of these is Q mod Z. So each of these is just a Z mod 2. So he asked, what is the ramification of this algebra? For which places do you get a 0? It's unramified. And for which places do you get a 1? And it's only finitely ramified. You get 1 finitely often. These various places. This is a direct sum. And the sum of the invariants has to be 0. There's an exact sequence from class field theory. And one thing he showed was that, so F is a non-CM form in this discussion. If the form is CM, then the endomorphism algebra is very different from what I just said, but also understood. It's much easier. Turns out that if F is that for a non-CM form, most primes are ordinary. So that means that if you look at the P Fourier coefficient, P does not divide AP. Right? AP is some sort of integer, P is in the index. Why should P divide AP? Doesn't happen. And you can generalize that definition. And he showed that at an ordinary place, if you're ordinary at that place, then you have to be unramified. You get a 0. Okay, so that's consistent with class field theory because most primes are ordinary and it has to go into the direct sum. Right? So I want to advertise now, do a little bit of blatant advertising for some of my papers. I'm going to leave a little quiz here. There are 3 papers called BG. The G is constant, but the B varies. And 2 of the B's are in this conference, so you have to hunt them out, or they'll be arriving in a few days at least. And there's one more paper called GGQ. One of the G's is not me. So we answered this question completely by saying that if this is X, and this is XV, we showed that XV is 0 if and only if, so I'm going to make this a rough statement, the valuation of AP squared, the same B here, this is some number which is in F, is congruent to 0 mod 2. So this has to be normalized to make it an integer. I'm not telling what the normalization is. I want to tell you this little result, which was worked out for, in many cases, in the first BG, then more generality in GGQ, and then some bad primes were also treated. The statement is a bit different in those cases. So I don't work in this anymore because it's more or less done. But I have to say that our proofs are very computational. They use some symbols. The Brauer group is given by symbols. So we just computed a lot of symbols and everything collapsed to a very simple formula. It's nice to have a more theoretical proof of this. That was my second remark. And third remark. So these AFs are abelian varieties of GL2 type. This is a statement that came out of the proof of Serre's conjecture by Harry and Wantenberger, Gisin. So every A, which is of GL2 type, has something to do with the endomorphisms. So I'm getting to the definition, is isogenous to one of these AFs. Simple, we have to use some words like simple, etc. So one thing you can ask, because the conference on modular curves, and in the elephant in the room is that this curve X non-split, which was introduced yesterday, we don't understand very well its rational points. Right? We're trying to prove this uniformity conjecture for many years. That if P is sufficiently large, then the image of the Galois representation attached to elliptic curve is GL2FP. If F is not a CM form, not a CM elliptic curve. Right? So you want to eliminate small subgroups in GL2FP, and this has been done. Jan is talking about the case of the Borel case where you have a rational point. And Serre himself did the case of exceptional groups, A4, S4, A5. And Perron, who I don't know if he's attending this anymore, if I was told he is. Perron and Bellou did the case of the non-split cartan. The non-split cartan is still open. So modulo that, it's done, but that seems a bit tricky. But one thing you can ask, and I asked this to Pierre Perron 10 years ago, is whether there was a Serre uniformity conjecture for these abelian varieties, AF. Right? So for elliptic curves, you have this conjecture. And we thought about it a bit, and it turns out to be totally false. You don't have any uniformity conjecture. Then we realized the problem was that we were allowing the dimensions of the abelian varieties to vary. In elliptic curves, the dimension is 1, it's fixed. So how about fixing the dimension of the abelian varieties to be 2, for instance? Only look at modular abelian surfaces. Then you can ask whether there's a conjecture, whether it makes sense to make a conjecture. And we couldn't find any obstruction, so we made that conjecture in a paper 10 years ago. And we also tried to prove this conjecture for the simplest case, the case that Serre did himself, and the case that Jan omitted because it's so easy. So it's not much of a paper, it's mostly an expository paper. So the case of A4, S4, A5, we could show that that case happens for only finitely many primes. So that's another remark I wanted to make. Okay, so